Hello everyone, this is Roshan and welcome to today's session which is week 6. So in this session we will cover two lectures, lecture number 15 and lecture number 16. So week 6 has two lectures. The first lecture is based on stress strain relation, and the second lecture is based on stress strain relation for isotropic material. Stress strain relation for isotropic material. So firstly, I will briefly give the overview of these lectures. That means some basic concepts, the important concept. So I simply write the formula here. I will not derive the whole derivation. I simply give the relation of that for of any formula which is in the lectures, and later on I will solve some problem based on this theory. So yeah, let's continue. So this the first lecture started on the relationship between stress strain. So the first thing that I want to discuss is linear stress strain relation. Linear stress strain relation. So as we know that stress and strain tensor both are symmetric tensor, and our goal is to express the stress in terms of strain, where each component of stress is a function of the strain value, and we know that it is a symmetric, so it has 6 independent strain, out of which 3 are symmetric actually. So basically it has total 9 component, and due to the symmetricity it has only 6 component. So we can write stress strain relation in terms of strain. So the linear stress strain relation for any material can be given by sigma ij. I am writing it in indices form. Sigma ij is equal to summation over k equal to 1 to 3 summation over L equal to 1 to 3 del sigma ij upon del epsilon kl into epsilon kl. So this is the expression for the linear stress strain relation, and this term is basically nothing the constitutive relation. This relation is also called as constitutive relation, and this denotes the stiffness of the material. This all denote the stiffness of the material. It can also be written in this way, that is sigma ij equal to summation over k summation over L C I J K L epsilon kl, where C I J K L is the stiffness tensor. This is actually stiffness matrix. So here you can see that it's free indices, that is IJKL, so it has total 81 components. Now let's do some calculation that is based on the symmetry. The independent constants basically reduces. So the first symmetry is the minor symmetry. So first here I will write independent independent components in tensor C. So it's actually a 4th order tensor. So I'm writing it here. The four bar expression in below the C denotes the 4th order tensor. So the first symmetry that is present in this relation is minor symmetry. So minor symmetry is nothing but basically this one.Cijkl is equal to Cjikl. This is because the stress symmetric matrix is symmetric. Actually, the stress matrix is symmetric. That's why I am writing it this way.Cijkl is equal to Cjikl. So using this, we have only using this symmetry we have only 6 cross 6, that means 6 independent constant. So using this symmetry we have only 36 independent constants. Also, we can also say that hereCijkl equal toCijlk. So this is due to strain symmetricity, that is epsilon kl is equal to epsilon lk. So these two symmetry, that we called as minor symmetry, due to this symmetry the actual 3 to the power, that means 3 to the power 4, that means 81 constant reduces to only 36 independent constant. Moreover, the next one is on my major symmetry. So major symmetry is coming from the strain energy density function. So I'm writing just the symmetry here. So actually the symmetry coming from the symmetricity of the uh, fourth order stiffness tensor, that is C m and kl bar is equal to half of ckl mn plus cmn kl is equal to half of cmn kl plus ckl mn is equal to ckl mn. So you can see here that is cmn kl now becomes, that is equal to ckl mn. So this is a major symmetry in stress strain relation, that comes from the strain energy density function. So using this symmetry, that is cmnkl is equal to ckl mn, we can say that out of 36 independent components here, only 21 are now independent. So due to this symmetry, out of 36 components, here, only 21 are independent. Okay, so we can say that total 81 independent constant, due to minor symmetry it reduces to 36 independent constant, and due to major symmetry it reduces to only 21 independent constant. So we can say that for any general isotopic material we have total 21 independent constant. From this we can say that general linear elastic material will have maximum 21 independent material constants. So basically sigma ij is related with Cijkl into epsilon kl. So if I and j are 6 component, that is and if we write it in Voigt notation, that means if you write in a component way, so we can write in this way: sigma 11, sigma 22, sigma 33, sigma 23, sigma 13, sigma 12 is equal to some 6 by 6 matrix which is called as stiffness matrix times the strain component is epsilon 1, epsilon 2, epsilon 11, epsilon 22, epsilon 33, gamma 23, gamma 13, and gamma 12. So this is the stiffness matrix actually, and so this is basically stress in terms of strain. And if you want to write the strain in terms of strain, so basically you have to take the inverse of this one. So we can also write this way, that is epsilon 11, epsilon 22, epsilon 33, gamma 23, gamma 13, and gamma 12 is equal to some matrix which is also a 6 cross 6 matrix, and this matrix is called as compliance matrix, or in tensor we say it compliance tensor, compliance matrix. Okay, times the stress component sigma 11, sigma 22, sigma 33, sigma 23, sigma 13, sigma 12. So this is all about the lecture number 15, which is based on a stress strain relation. Now the next lecture, the topic is on stress strain relation for isotropic material. So we know from the previous lecture that the stress strain relation, in the stress strain relation we have total 21 independent constant in the stiffness matrix for any general isotropic material. So for the case of isotropic material, we have same property in all the same direction at a given point. So from this expression we can now find the stress strain relation for the isotropic material. So for the isotropic material we have two independent elastic constant. So stress strain relation for isotropic material, stress strain relation for isotropic material. Stress strain relation for isotropic material, it is given by this relation: sigma ij equal to lambda times trace of epsilon times del ij plus 2 mu epsilon ij. We can also write in this way: sigma ij is equal to lambda of trace of epsilon is given by epsilon 11 plus epsilon 22 plus epsilon 33 times delta ij plus 2 mu epsilon ij. So this is the stress strain relation for isotropic material. Okay, and from here we can say that it has only two independent elastic constants, that is lambda and mu, where lambda and mu are the Lamis parameter. Alternatively, we can express it in component form. So I simply just write here this expression in the component form. Also, we can relate the strain in terms of stress. As I said earlier, that we can do it also. The matrix that is formed using that way is the compliance matrix. So I'm writing just the strain in terms of stress. So the component so first of all, I will write here that strain can be expressed in terms of stress. It is called as sorry. It is called as three-dimensional Hooke's law. Three-dimensional Hooke's law. And it is given by this relation. So I am right here just the component of each component of a strain in terms of stress. That is epsilon 11, that is longitudinal stress. Strain along even direction is given by 1 by E sigma 11 minus mu times sigma 22 plus sigma 33. Similarly, we can write epsilon 22, that is 1 by E sigma 22 minus nu times sigma 11 plus sigma 33. In the same way, we can write epsilon 33, that is 1 by E sigma 33 minus nu times sigma 11 plus sigma 22. And the other three shear strain is given by this relation, that is gamma 13. So gamma 12 is given by 2 times epsilon 12, which is equal to sigma 12 upon g, that is tau 12 upon g. Similarly, gamma 13 is given by gamma 13 upon g, and gamma 23 is given by gamma 23 upon g. So this sixth component is called as the three-dimensional Hooke's law. So this relation can be used in solving many problems based on stress-strain relation for isotropic material. And here E is the Young's modulus of the material. The E that is shown here is the Young's modulus of the material, and nu is the Poisson's ratio. So I can relate the Young's and G is the shear modulus of the material. So we can relate the Young's modulus, shear modulus, and the Poisson's ratio in term with respect to each other. So the relation between the Young's modulus and the shear modulus is given by this relation, that is G equal to E upon 2 times 1 plus nu, where nu is the Poisson's ratio. So this is the relation for the shear and the Young's modulus. And also from the Lami's parameter, we can say that the second Lami's parameter is equal to shear modulus, that is G equal to mu. The next is Poisson's ratio. So Poisson's ratio is basically defined as the ratio of the induced lateral strain upon the imposed longitudinal strain. Suppose we have stretch a uniform rod, or we say a beam or a bar, or we can say a bar along uniaxial stretch. We can provide it. So on stretching it along x1 direction, we can say that there is a stretch developed in the bar along x direction, and there is also some compressive stress developed along the lateral direction, and due to this there is some compressive strain developed in the lateral direction also. So we can say that as we elongate the beam along x direction, there is some compressive strain developed in the lateral direction, and these two can be related using a ratio that we called as Poisson's ratio, which is given by nu is equal to negative of induced strain, induced lateral normal strain upon imposed longitudinal strain. So this is also called as the Poisson's effect, imposed longitudinal strain. Okay. That we can say that epsilon 2 that is normal shear strain along y direction is equal to minus nu times imposed longitudinal strain in x direction. The next topic that I want to discuss is the bulk modulus of elasticity. Bulk modulus of elasticity. So bulk modulus is given by minus delta P upon delta V upon V, where delta P is the pressure change due to change in delta P is the pressure change and delta V is the volume change. And we know that as according to we also studied in the earlier lectures that the change in volumetric strain is nothing but the trace of the strain tensor. So delta Vy is the volumetric strain and this is given by trace of strain tensor, which is equal to epsilon 11 plus epsilon 22 plus epsilon 33. And we can also relate the bulk modulus, that is K, with the shear modulus and the Young's modulus. So I just write here the relationship between the bulk modulus and the Young's modulus. So it is given by K is equal to E upon 3 times 1 minus 2 nu, where nu is the Poisson's ratio. So this is the relation between the bulk and the Young's modulus. The next thing that I want to discuss is the limiting case of the Poisson's ratio. So the Poisson's ratio can't be less than -1 and can't exceed the value of 1 by 2. So it ranges from -1 to 1 by 2. And for incompressible material where bulk modulus tends to almost 0, that means on incompressible material we can say that K becomes infinity, because here you can see that delta V, that is change in volume, is equal to 0, so it becomes infinity. And for it to become it infinity, this expression, that is a denominator in this expression, should become 0. And for this to become 0, 1 minus 2 mu must have 0, which means that nu is equal to 1 by 2. So this is the case of incompressibility for incompressible material where the change in volume is 0, and for that case nu should be taken as 1 by 2. So this is all about the isotropic material. The next thing that I want to discuss, and I say that for isotropic material, for a general anisotropic material, we have 21 independent elastic constants, and if we say about the isotropic material, it has only 2 independent elastic constants. Now we will talk about the transversely isotropic elastic material. Transversely isotropic elastic transversely isotropic material. So for transversely isotropic material, we have 5 independent elastic constants. 5 independent elastic constants. For transversely isotropic material, the property is same along any one direction. So we have 5 independent elastic constants for such kind of material. There is also another type of material, that is orthotropic material, that we say orthotropic material. For this type of material, actually the two fibers have different properties. So it has basically 9 independent elastic constants. The best example is wood. Wood generally obey the constitutive relation of orthotropic material, and therefore it has 9 independent elastic constants. 9 independent elastic constants. So this is all about these two lectures, which is already discussed in the lecture in detail. And for the detailed derivation, you can refer to the lectures, which is already available in the NPTEL website. Now I will move on to the problem solving session. So the first problem, I write on the first problem here, problem 1. So I will solve some problem based on these two lectures, from which you can see that these concepts can be used in solving different types of problems based on the elasticity for isotopic material and for the general material also. So the first question is, think of a rubber cube which is inserted within a cavity in steel block. The cavity has the same form and size as that of rubber cube, which is also shown in the figure. I will draw the figure later on as shown below. The top surface of rubber cube is pressed by another steel block with a pressure of P Pascal. Assume the steel to be rigid. And that there is no friction. Between steel and rubber. So the question is, the first part of this question is, find the relation between normal stresses in x and y direction in this problem. And the second part of this question is, find the volumetric strain. Find the volumetric strain. Okay, so this is the figure that is given in the question. So this is the steel and this is the rubber actually. So here there is no fixed thing that is free to move, and it is of width L, and the direction is given here. This is along y-axis, this is along z-axis, and this is along x-axis. Okay, so I am reading the question one more time. Think of a rubber cube which is inserted within a cavity in a steel block. So here there is a cavity, you can see here, and there is a rubber cube which is inserted in this cavity. Okay, the cavity has the same form and size as that of the rubber cube. The cavity that is the rubber cube that is inserted in the cavity has the same size and form. That means there is no free space available in this cavity after the rubber insertion. The top surface of the rubber cube is pressed by another steel block with a pressure of P Pascal. So the top surface is pressed by some pressure P Pascal. That is, it is pressed by some pressure P Pascal. Okay. Assume the steel to be rigid. Okay, we are assuming that the steel to be rigid, and that there is no friction between the steel and the rubber, and also there is an assumption that there is no friction between the steel and rubber. Find the relation between the normal stresses in x and y direction in this problem. So we have to find the normal stresses in x, that means the relation between the normal stresses in x and y direction in this problem, and the second part of this question is find the volumetric strain. So let's start the problem. So this is along x direction, this is along y direction. As we can see that rubber ball is constrained to move in the x direction and move in the y direction. Only it can move along the z direction because there is no boundary in between that. If we apply some pressure, so the strain will be there along z direction, and there will be no strain along y and x direction because this is constrained out from outside. That's why we can say that the displacement along x direction, so the solution, displacement that is u at x equal to 0, similarly u at y equal to 0, and there is some stress, there is some displacement can happen along z direction. As you can see that it may be a function of x and y. So we can say that uz is there and it is not equal to 0, and it can be a function of x, y and z both. Furthermore, as we can see that, as also mentioned in the question, that the rubber cube is pressed by another steel block with a pressure of P Pascal. So it has uniformly pressed by some pressure P Pascal, and from this also there is no movement along x and y direction. So we can say that the displacement along z direction is also only depend on the z coordinate. That means there is no that means the displacement component uz is independent of x and y coordinate. That is, we can write as uf z any x, y, z is equal to u at z. That means it is independent of the coordinate x and y. Now we can say that as there is no strain developed along x direction and along y direction. So there is only one strain which is available along z direction, that is epsilon zz, because there is some pressure, uniform pressure acting from the upward of this tube. So we can say that there is only single strain, single longitudinal strain which is acting downward, which is epsilon zz. So we can write the stress tensor, that is component of stress tensor. So stress tensor component, stress tensor epsilon component, it will become epsilon equal to, so it has only the longitudinal strain along z direction, so all the components are 0 except the last one, that is epsilon zz. So what the question is, what we have to find is the relation between the normal stress in x and y direction in this problem. So basically we have to find the stress. So first we have to find the value of the strain, then we have to find the value of stress. So as in the question it is mentioned that the rubber yeah, so we are assuming that the rubber behave as a isotropic material, so we can write from the constitutive relation the shear stress in terms of shear strain, which is given by tau xy equal to gamma xy upon g, which is 0 because there is no gamma xy, and gamma zz is given by gamma zz upon g, sorry, tau zz, gamma zz upon g, which is gamma zz is epsilon zz. So we're not talking about the gamma, we're talking about actually tau xz. So we can say that tau xz, because there is no gamma xz component, so that's why it is 0, so it also becomes 0. The next is tau yz, so it is also given by gamma yz upon g, which is again 0, so it is also equal to 0. So the question is relation between the normal and normal stress in x-y direction. Now we can see that all the shear stress component vanish, and only thing that we have left is the normal stresses. And from the symmetry of the stress tensor, we can say that sigma xx equal to sigma yy. And you can see from the figure, because it is constrained along x and y direction, so there is no strain along x and y direction. So we can say that epsilon xx equal to 0, which means, and we know the relation between the strain and the stress from these equations, that is epsilon xx equal to 1 by e sigma 11 minus nu times sigma 22 plus sigma 33. So it is given by epsilon xx equal to 1 by e sigma xx minus nu times sigma yy plus sigma zz. And we know from the question that epsilon xx is 0. Similarly, sigma yy and sigma zz. So sigma yy is equal to sigma xx. So we can say from here that sigma xx, which is nothing but also equal to sigma yy, is equal to nu times sigma zz upon 1 minus nu. So this is the relation between the normal stresses Now the next question is, find the relation between normal stress in x y direction. We have found the relation between the normal stress in x y direction. It is equal. The next question, you find the volumetric strain. Now here, as you can see that this is stress in terms of the longitudinal strain along z direction. So we have to find the value of sigma zz in terms of the parameter that is given the question. So for this we have to use some other boundary condition also. So let's apply the traction boundary condition on the boundary itself. So from this we can say that traction on top face is equal to external pressure at top face, because here you can see in the question that there is some pressure, external pressure applied at the boundary, that is P, and from internal there is some stress developed due to this pressure. So the only that is only I have written here, that is traction on the top face equal to external pressure at the top surface, and it is along E3 direction. So we can find the traction along the E3 direction, that is given by sigma dot E3, sigma dot E3 equal to external pressure at top surface. So what is the external pressure acting? So the first pressure is acting, that is the pressure itself, that is P, and the other thing that is acting, because in the question nothing in nowhere mentioned that we are neglecting the gravitational force, the force, the stress developed due to the gravitational force. So the gravity, that is the G acting downward, so we can write the stress due to gravity, that is the first I write here, pressure P plus, and the gravity, due to gravity the total stress is given by rho g h. Okay, and the direction of this one, because if we assume that the upward direction is taken to be positive, so the downward direction is taken to be as negative. So the upward direction is the stress direction, and the downward direction is the external force direction. So as it is downward direction, so it is given a minus times E3. Okay, so if you multiply the sigma tensor with if you dotted the sigma tensor with E3, we get tau xz, tau yz, sigma zz, which is equal to 0 0 minus minus P plus rho gh. Okay, so this is the expression for sigma zz, which is given by minus of P plus rho gh. Simply using this equation we can write the expression of sigma xx and sigma yy. So sigma xx, which is equal to sigma yy, is given by nu upon 1 minus nu minus of nu upon 1 minus nu P plus rho g h. So this is the final expression for the stress along x and y direction. Now the second question is, find the volumetric strain. So here from in the beginning we say that so what is the question? Find the volumetric strain. You can say that the volumetric strain is given by the trace of stress tensor, which is nothing but the summation of the diagonal element, that is epsilon xx plus epsilon yy plus epsilon zz. And here in the question it is mentioned that the epsilon xx and epsilon yy value are 0, so only we have to find is the epsilon xx, epsilon zz. So epsilon zz is given by using the stress strain relation, that is this equation. Using this equation, epsilon zz equal to epsilon zz equal to 1 by e sigma zz minus nu times sigma xx plus sigma yy. So this is written according to the constitutive relation that we have for isotopic material, which is equal to 1 by e, and sigma xx and sigma y are equal, so therefore we can write this way: sigma zz minus 2 nu sigma xx, then 1 by e sigma zz minus 2 nu, and what is sigma xx? We found here minus nu times there, so it becomes minus nu times, that is nu square upon 1 minus nu times sigma zz. Okay, so this is expression for epsilon zz in terms of sigma zz. If we take the LCM, we will get 1 minus nu minus 2 nu square upon 1 minus nu times sigma zz, which is equal to epsilon zz. Now the volumetric strain, which is the second part of this question, is given by the volumetric strain is given by epsilon, that is epsilon v, epsilon 11 plus epsilon 22, or we say epsilon xx plus epsilon yy plus epsilon zz, and these two are 0. The only thing that is left is epsilon zz, which is given by this relation 1 by e 1 minus nu minus 2 nu square upon 1 minus nu times, because sigma zz is also here, which is p plus rho g h. So this is expression for volumetric strain. I hope everyone is understanding these concepts. It is a very good question, by the way. So this is all about question number 1. Now let's move on to the next question, that is problem number 2. Problem 2. So please see the above solution for the previous problem, so that you can think in a better way. If you have any doubt, please write in the chat box, or even you can unmute yourself so that I can listen you. So I am writing the next question, that is think of a thin rectangular plate being compressed along its 4 edges, but not allowed to expand or contract expand or contract in its thickness direction. Assume the thickness direction is along z-axis. Assume the thickness direction is along z-axis. The following components of stress and strain matrices are given. Which is sigma xx equal to sigma yy equal to minus p, and tau xy equal to tau yz equal to tau zx equal to 0, and epsilon zz equal to 0. So the question is, assuming the material to be isotropic, find out the remaining components of strain matrix. Okay, so I am repeating the question once again. So the question is, think of a thin rectangular plate being compressed along its four edges but not allowed to expand or contract in its thickness direction. So there is no deformation along the thickness direction. Assume the thickness direction is along z-axis. So here there is an assumption that the thickness direction is along z-axis. The following components of stress and strain matrix are given. So these are the component of stress, some component of stress and strain matrix, which is given here. So the question is, assuming the material to be isotropic, find out the remaining component of strain matrix. So we have only one strain matrix component given here, that is epsilon z which is equal to 0. So the question is, suppose we have one rectangular plate, thin rectangular plate actually, and it is compressed along all the four directions. And it is mentioned in the question that stress along x and y direction is minus p, and tau xy, tau z, and tau z is 0, and epsilon z is 0. And the axis is given in this way, that is, this is along y direction, this is along z direction, and this is along x direction. So coming to the solution part, as mentioned in the question that it is not allowed to expand or contract in the thickness direction, so we can say that the displacement along thickness direction is 0, that is uz equal to 0, and therefore we can say that epsilon that is longitudinal strain along z direction is also 0. Now we have only so epsilon z is 0 also is given in the question. Now we have to determine the other 5 strain component, epsilon xx, epsilon yy, gamma xy, gamma yz, and gamma zx. So we are using here the stress strain relation for the linear isotropic material. So the first one is gamma xy. Gamma xy is given by tau xy upon z, and tau xy is 0, so therefore gamma xy is also 0. Similarly, gamma yz, gamma zx are equal to 0. Now we only have to find the relationship between epsilon xx and epsilon yy, and all the three terms and all these three terms are 0. So for this we are using the constitutive relation, that is relation between sigma xx and sigma zz. So epsilon zz in terms of sigma zz is given by 1 by e sigma zz minus nu times sigma xx plus sigma yy, and sigma xx and sigma yy are equal, and epsilon zz equal to 0. So we can say that sigma zz equal to minus, that is nu times sigma xx plus sigma yy. And what is sigma xx and sigma yy? As given in the question, it is minus p. So minus p, that is minus 2p, and times upon, and it is multiplied with nu, so it becomes minus 2 nu p. So sigma zz is given by minus 2 nu p. Now we have to find the epsilon xx and epsilon yy. So the stress strain relation in terms of epsilon xx and epsilon yy is given by, epsilon xx is given by 1 by e sigma xx minus nu times sigma zz plus sigma yy. Similarly, sigma yy is given by 1 by e sigma yy minus nu times sigma xx plus sigma zz. So epsilon xx, what is epsilon xx? Epsilon xx, we have to find it. So epsilon xx equal to 1 by e, and sigma xx is given by minus of p. Yeah, it's minus of p minus nu times, what is sigma zz is minus 2 nu p. What is sigma yy is minus p, which is equal to minus p upon e, minus p upon e 1 minus nu times 2 nu plus 1. Okay, which is equal to epsilon xx is equal to minus of 1 minus nu times 2 nu plus 1 upon e times p. So this is the relation for the longitudinal strain in terms of p and nu and e. And from this relation you can see that if you find the value of epsilon yy, you will get the same result. I am just writing here, that is epsilon yy is nothing but equal to epsilon xx. Okay, so this is so for using the stress strain relation and the given condition in the question, we have found the value of the different strain measures. So sigma tau xy, gamma xy, gamma yz, and gamma zx is equal to 0, and the remaining sigma epsilon xx and epsilon yy is given by this relation, that is minus of 1 minus nu times 2 nu plus 1 upon e times p. So there is one more bracket. So this is all about question number 3, sorry, problem number 2. Now coming to the next problem, that is problem number 3. So problem 3. So this question says that, so that in case of isotropic bodies, the stress tensor and the strain tensor, the stress tensor and the strain tensor will both have same set of principal strain, same set of principal directions. Same set of principal directions, further show that the set of planes whose normals are sorry, whose normals are parallel to one of the principal directions to one of the principal directions do not slide relative to each other. Do not slide relative to each other. So the question is, so that in case of isotropic bodies, the stress tensor and the strain tensor will both have same set of principal directions, further so that the set of planes whose normals are parallel to one of the principal direction do not slide relative to each other. So we are assuming that and we know from the previous lecture that the eigenvalue of the strain tensor will give us the principal value of the strains. So we are using that concept, that is eigenvalue problem. So the solution is eigenvalue problem for a strain is, so the strain tensor times the principal direction is given by some alpha value, that is the principal strain times the principal direction. So it can be written when we have to find the value of the principal strain and the principal strain direction. So here n is the principal strain direction, n is the principal strain direction, n is the principal strain direction, and alpha is the principal strain component, and alpha is the principal strain component, and alpha is the principal strain component. Okay, so here we have to prove that the strain tensor will both, the stress and the strain tensor will both have same set of principal direction. So there is a relation between the stress and the strain that is called as a stress strain relation. So I am using this relation, that is using the stress strain relation, using the stress strain relation, one can write a stress tensor as sigma equal to lambda times trace of epsilon, trace of sigma, trace of epsilon times identity plus 2 mu epsilon. So this is actually a stress strain relation for isotropic material. Now post multiplying this expression with strain normal, and so that is post multiplying above equation with principal strain normal n, with principal strain normal n. So it becomes sigma times n equal to lambda times trace of epsilon times identity times n plus 2 mu epsilon times n. Okay, and it becomes lambda times trace of epsilon times n plus, what is epsilon n? So from this relation we can say that epsilon n is equal to alpha n. So it becomes 2 nu alpha n. And if we take n common from both the terms, we will get lambda times trace of E into identity plus 2 mu alpha times n. And you can see here that it is nothing but the principal stress value. It is nothing but the principal. It will give us the, because it is in terms, now it is in terms of sigma n equal to some value times n. So using the eigenvector analysis, we can say that it is nothing but the principal stress component. And here we can see that we have to show that the set of planes whose normals are parallel to one of the principal plane do not slide relative to each other, and the question has, we have to prove the stress tensor and the strain tensor will both have the same set of principal direction. So you can see here from this equation and from this equation both have principal direction same, that is n is the common in both the equation. So we can see that normal vector n also turns out to be principal direction, also turns out to be principal direction for stress tensor sigma, for stress tensor sigma. Okay, so this is all about question number 3, that is problem 3. Now move on to the next question, that is problem number 4, and the question is, a sample is subjected to a sample is subjected to a biaxial test under plane strain condition, plane stress condition. A sample is subjected to a biaxial test under plane stress condition. For plane stress, there is no stress along z direction, normal stress along z direction, that is sigma zz equal to 0, and also along with that the shear stress coming in the shear stress along z direction is also turns out to be 0, that is tau xz tau yz equal to 0. Using a sample is subjected to a biaxial test under plane strain condition using a special loading frame that maintains an in plane loading constraint of sigma xx equal to 2 sigma yy. So there is a loading constraints so that it can behave as a plane strain condition that maintains an in-plane loading constraint of sigma xx equal to 2 times sigma yy. So we have three questions based on this statement. That is, the first part of this question is find the slope of sigma xx versus epsilon xx. The next part of this question is find the ratio between epsilon xx and epsilon yy in terms of nu. In terms of nu. And the third part of this question is find the ratio between epsilon zz and epsilon xx. So the question is, I am repeating the question once again. So the question is, a sample is subjected to a biaxial test under plane stress condition where sigma zz, tau xz and tau yz equal to 0 using a special loading frame that maintains an in-plane loading constraints of sigma xx equal to 2 times sigma yy. Find the slope of the sigma xx versus sigma epsilon xx. So the first part of the question is we have to find the slope of the epsilon xx versus sigma xx, and the second part of this question is find the ratio between the epsilon xx and epsilon yy in terms of nu. That is, we have to find the ratio of epsilon xx and epsilon yy in terms of the Poisson's ratio. And the last part of this question is find the ratio between epsilon zz and epsilon xx. So the last question is to find the ratio of epsilon zz and epsilon xx. So let's move on to the solution part. So it is subjected to plane stress condition, no? So I will draw the figure also. Plane stress condition only, so there is no force acting on the z direction. So this is a figure for the plane stress condition. Now the first question is the slope of sigma xx upon epsilon xx. So the sigma xx upon epsilon xx. This is the first part of the question. So first we have to write down the epsilon xx value in terms of the sigma xx value. So epsilon xx using the stress strain relation for isotropic material, epsilon xx is given by 1 by e sigma xx minus nu times sigma yy plus sigma zz. And from the question it is given that sigma zz equal to 0, and it is also mentioned in the question the relationship between the sigma xx and sigma yy. So 1 by e, and what is sigma yy? If we take the ratio of epsilon xx with respect to sigma xx, so it is given by 1 minus nu times sigma yy upon sigma xx. So here, from here, sigma xx upon epsilon xx is given by E upon 1 times nu minus del sigma yy upon sigma yy upon sigma xx. Okay. And it is given in the question that sigma xx equal to 2 times sigma yy. So it is nothing but E upon 1 minus 2 nu. Okay. The next part of the next part of the question is we have to find the ratio of epsilon xx and epsilon yy. So epsilon yy in terms of epsilon xx, it is given in terms. First we have to write the stress strain relation. So 1 by E sigma yy minus nu times sigma xx plus sigma zz. From here we can see that sigma zz is 0. So epsilon yy upon sigma xx, if we take the derivative, if we take the ratio of epsilon yy with respect to sigma xx, we will get 1 by sigma yy upon sigma xx minus nu. And what is sigma yy upon sigma xx? Now we are multiplying the both two equation, that is equation number 1 and equation number 2. Multiplying equation 1 and 2, that is sigma xx upon epsilon xx times epsilon yy upon sigma xx equal to E by 1 minus 2 nu into E upon 1 by E. What is sigma yy upon sigma xx? That is 2 minus nu. So from here it will cancel out, and also from the right hand side this will cancel out. So the final term that will remain is epsilon yy upon epsilon xx, which is equal to 2 minus nu upon 1 minus 2 nu. So this is the expression for epsilon yy upon epsilon xx, and this is the expression for sigma xx upon epsilon xx. Okay, and the last part of the question is find the ratio between the epsilon zz and epsilon xx. Epsilon zz by epsilon xx. So we have to write the stress strain relation of epsilon zz in terms of the stress. So it is given by 1 by sigma zz minus nu times sigma xx plus sigma yy, and it is 0 by according to the question. So if we take the ratio of epsilon zz with respect to sigma xx, so it is given by epsilon zz upon sigma xx equal to 1 by minus nu times sigma xx will become 1, and sigma yy upon sigma xx is 2. So it will become 1 by E minus 3 nu. And if we multiply this equation, that is equation number 3, with equation number 1, so epsilon zz upon sigma xx multiply by sigma xx upon epsilon xx equal to minus 3 nu by E times E by 1 minus 2 nu. E by 1 minus 2 nu. E will get cancel out, and this will also cancel out sigma xx. So the final term that will remain is epsilon zz upon epsilon xx equal to minus 3 nu upon 1 minus 2 nu. So this is the ratio of epsilon zz upon epsilon xx. So we have to find three part of this question, and we found out all the three one. The first part is to find the ratio of sigma xx and epsilon xx. The second part is to find out the ratio of epsilon yy upon epsilon xx, and the last one part is to find out the epsilon zz and epsilon xx. So this question is complete now. Now let's move to the next question. So this is problem number 4. Now the problem number 5 is problem 5. Think of an isotropic think of an isotropic think of an isotropic square plate which is clamped along one of its edges and subjected to uniform normal compressive load. On the edge opposite to the clamped end. Opposite to the clamped edge. The other two edges are traction free. Suppose that no out of plane displacement. Suppose that no out of plane displacement generates. The question is, furthermore, the displacement component ux and uy are not function of z either. The displacement component ux the displacement components ux and uy are not functions of z either. Are not function of z either. So this is a statement of this question, and the problem on this statement is to find the first part of this question is write down the strain and stress matrix for this problem. Write down the strain and stress matrix for this problem. And the next part of this question is show that jet component of stress equilibrium equation is automatically satisfied. And the next part of this question is what boundary conditions will be used to solve this problem? Will be used to solve this deformation problem. What boundary condition will be used to solve this deformation problem? So this is a very good question actually. So I am just reading the question one more time. So the question is, think of an isotropic square plate which is clamped along one of its edges and subjected to uniform normal compressive load on the edges opposite to the clamped edge. Okay. The other two edges are traction free. There is no traction acting on the other two edges. Suppose that no out of plane displacement generates. There is an assumption that there is no out of plane displacement generates in this case. Furthermore, the displacement components ux and uy are not function of z either. Here also the displacement component ux and uy are also not a function of z. So based on this statement, the question is write down the strain and the stress matrix for this problem. The first part of this question is we have to write the stress and the strain matrix. The second part of this question is so that z component of a stress equilibrium equation is automatically satisfied. We will see that in this question z component of a stress equilibrium equation is automatically satisfied. And the last part of this question is what boundary conditions will be used to solve this deformation problem. Okay, so let's start the solution for this problem. So first I will draw the figure for this problem. So there is a clamped edge where there is no deformation happen. And there is a compressive force acting along these edges, and this is actually fixed. Okay, and the direction is given by this way: x, y, and z. Now in the question it is mentioned that the out of plane displacements along z-axis is 0. So from there we can say that uz equal to 0. Furthermore, it is mentioned that the displacement component ux and uy are not functions of z either. So from this we can also say that ux is only a function of x and y. Similarly, uy is also a function of only x and y. So First part of the question is to write down the stress and the strain matrix for this problem. So the resulting strain matrix, first part of the question is, so the strain component of strain tensor is epsilon equal to epsilon x, epsilon y 0, epsilon xy, epsilon yy 0, 0, 0, 0, because there is no strain along the z direction, and it is given by del u by del x half of del u by del x, sorry, del u x upon del x, del u x over del y plus del u y over del x 0, half of del u x over del y plus del u y over del x, del u y over del y 0, 0, 0, 0. In this figure, we can see that if there is a compressive stress, compressive force acting along x direction, minus x direction, so there, and also in the question it is mentioned that there is no strain developed along the z direction. So we can say that it's a condition of plane strain condition, where all the components associated with the out of plane deformation are 0. That means epsilon z equal to 0, gamma xz equal to 0, gamma yz equal to 0. So I'm writing this case that this condition represents plane strain condition. Plane strain condition therefore all the components associated with out of plane direction are 0. That is epsilon zz equal to 0. Similarly, gamma xz, which is given by del u x over del z plus del u z over del x equal to 0. Also gamma yz, which is given by del u y over del z plus del u z over del y equal to 0. Also in the question it is mentioned that the stress strain relation is isotropic. So for isotropic linear stress strain relation, we can see that we can write down the stress matrix in terms of because the stress matrix is given by this one, sigma is given by, for the plane strain condition, sigma xx tau xy 0, tau xy sigma yy sigma zz 0, 0, 0. And if we want to write this stress matrix in terms of strain matrix, so we have to use the linear stress strain relation for isotropic material, which is given by, if we write down the components, each component, so it is given by lambda plus 2 mu epsilon xx plus lambda times epsilon yy. Tau xy is given by 2 mu epsilon xy, it is given by 0, it is equal to 2 mu epsilon xy, sigma yy is given by lambda plus 2 mu epsilon yy plus lambda times epsilon xx, and epsilon sigma zz is given by lambda times epsilon xx plus epsilon yy. So this is the stress relation in terms of the strain value. And we also say that earlier that for the plane strain condition, the stress, the longitudinal stress along that direction is not zero. So for that condition, we can say that sigma zz is not zero. Therefore, it has some value that is equal to lambda times epsilon xx plus epsilon yy. However, out of plane displacement is zero, that is uz equal to zero, which means that there is no displacement along z direction. That means there is some constraint which is acting along z direction, and that's why it's not moving. So there must be an internal stress which is acting opposite to the applied stress, which is acting opposite to the applied force. So we can say that there is some compressive stress also on the jet face. So this is the first question, I guess. Yeah, write on the strain and the stress matrix for this problem. So we have written here the stress matrix. This is nothing but the strain matrix, and this is the stress matrix for this problem. Okay, so the first part of this question is completed now. Move on to the second part of this question, which is to show that the jet component of a stress equilibrium equation is automatically satisfied. So first I have write on the jet component of a stress equilibrium equation, which is given by del tau zx upon del x plus del tau zy upon del y plus del sigma zz upon del z plus 0 equal to 0. As per the question, it's a plane strain problem along z direction. So there is no strain along z direction, and due to this, the shear stress along z direction is also 0. So this two becomes 0. The only term that will remain is del sigma zz upon del z equal to 0. And what is del sigma zz upon del z is lambda times epsilon xx plus epsilon yy upon dz equal to del z equal to 0. And what is epsilon xx? So here we have to take the derivative of epsilon xx and epsilon yy with respect to z. But here we found that the epsilon xx and epsilon yy is independent of the x and y coordinate, because the displacement ux and uy are independent of the z coordinate, and therefore from this assumption we can say that the longitudinal strain epsilon xx and epsilon yy also independent of the z direction. So it ultimately satisfied, because here also it becomes 0. So from here we can say that LHS equal to RHS, which is equal to 0. So I am writing here, this is because epsilon xx and epsilon yy are not function of z. So the stress equilibrium equation for z direction is automatically satisfied for the plane strain condition. Satisfied for the plane strain. Satisfied for the plane strain condition. For the plane strain condition. Now the third part of this question, that is, what boundary condition will be used to solve the deformation problem? So to solve any deformation problem, we can use displacement boundary condition or we can use traction boundary condition. So we have to use on either side of the boundary of this plate. So to solve, I'm just writing here the displacement and traction boundary condition. The displacement and traction boundary condition that will be used to solve this problem are as follows. So first, so here I am just mentioning that both the boundary condition can be used on the either side of the boundary. So the first, so it has actually 6 faces. So yeah, so first, suppose I am asking that it is at 0, at x equal to 0, we can apply one displacement boundary condition. So this is suppose phase 1. This is suppose phase 2. This is phase 3, and suppose this is phase 4. So we are applying displacement boundary condition. Displacement boundary condition on phase 1. Here you can see it is fixed or clamped. So the displacement at x direction, at x equal to 0, at any y or z equal to 0. Similarly, displacement along y direction at x equal to 0 and at any yz, it's also equal to 0. So this is a boundary condition which is acting on the phase 1, which will be applied on phase 1. Next, in phase 2, you can see that phase 2 is free to move, so we can apply here traction boundary condition. That is a traction boundary condition, yes, of course. So it can move freely, so here we can apply traction boundary condition on phase 2. So it is given by stress tensor, because we have to find the traction along E2 plane. So sigma dot E2 at phase 2. So it is given by tau xy, sigma yy, and sigma zy, or we say tau zy. From the equation it is given that tau xy, so yes, what is tau xy? Is it tau xy or something else? Because is there any shear stress acting on the, so it is a traction free boundary condition because there is no shear, because there is no external load acting on this phase, so it's actually a traction free boundary condition. So we can say that tau xy equal to 0, sigma yy equal to 0, and tau zy equal to 0, because it's a traction free. Now coming to the phase 3. So phase 3, you can see that there is one force is acting, compressive force is acting along x direction. So here, due to this, traction is being developed on this edge. So here we can also apply traction boundary condition, but it's not a traction free boundary condition. So traction boundary condition on phase 3. So on phase 3, it's along the x direction. So we can write sigma dot E1 at phase 3 equal to sigma xx tau xy and tau xz. So as you can see that stress pressure P, suppose this is pressure P, and it's acting along the negative of x direction. So we can say the traction here equal to minus of P along x direction. Tau xy, there is no shear along x direction, so it's equal to 0, and there is no shear along x direction also in the xz plane, so it's also 0. So this is the traction boundary condition on phase 3. Now coming to phase 4, there is no stress developed in this phase also, because there is no traction applied on this phase, therefore it's also a traction free boundary condition on phase 4. So it is given by traction boundary condition on phase 4. So we have to multiply it along E2 or minus E2. Let me check. So this phase is actually downward, the phase normal is downward, but the direction that we have taken is along upward, that is y is along upward direction. So we can take with respect to minus of E2. We have to take the dot product with respect to minus of E2. Sigma dot minus of E2 at phase 4. So this is also a traction free boundary condition. So it will become tau xy minus sigma yy minus tau xzy. So it will ultimately become 0 because it's a traction. There is no external pressure or force acting in this on this phase. So it's also a traction free boundary condition. So the last question is, what boundary condition will be used to solve this deformation problem? So we have written all the boundary condition that will be used to solve this deformation problem. So using this, so we have to simply use this boundary condition to find out their knowns when we solve the partial differential equation of the stress equilibrium. When we solve the equilibrium equation, we will get some constants on integrating them. Then we have to find this constant using the boundary condition. So using this, we can solve the complete deformation problem. So this is all about question number 5. That is problem 5, of course. Yeah. So this is problem 5. Now move on to the next question, which is a multiple choice question type. That is problem number 6. Yeah. This question is, which of the following is a dimensionless quantity? Problem 6. Which of the following is a dimensionless quantity? The options are shear stress, Poisson's ratio, strain, or the option D is none of these. No. Which of the following is a dimensionless quantity? Shear stress. No, stress is not a dimensionless quantity because it is given by force per unit area. So this option is incorrect. Poisson's ratio. Yeah, this is a ratio. In the name also it is mentioned the ratio, and ratio is also always a dimensionless quantity because it's something that we have to take with the same because it's equal to minus of lateral strain upon longitudinal strain, and strain itself a dimensionless quantity, so that's why it's the correct option. Strain, yeah, strain is a dimensionless quantity, so it's also a correct option. None of these, because we have two correct options, so this is also not a correct option. So this is problem number 6. Problem number 7 is, Poisson's ratio is Poisson's ratio is, options are negative of, sorry, negative of lateral strain upon longitudinal strain. The next option is longitudinal strain upon lateral strain. The third option is a dimensionless quantity. A dimensionless quantity. And the fourth option is a dimensional quantity. So as I mentioned above, Poisson's ratio is negative of lateral strain upon longitudinal strain. Yes, it's a correct option. The next option is longitudinal strain upon longitudinal lateral strain. No, this is incorrect. A dimensionless quantity. Yes, Poisson's ratio is a dimensionless quantity. The last option is a dimensional quantity. No, it's an incorrect option. No. Problem number 8. Which of the following holds true? Which of the following holds true? The option, first option is the compliance matrix. The compliance matrix is obtained from the transpose of stiffness matrix. The compliance matrix is obtained from the compliance matrix is obtained from inverse of stiffness matrix. The third option is, sorry, not inverse, negative of stiffness matrix. The third option is the compliance matrix is obtained from edge is obtained from, sorry, compliance, here it's compliance. The compliance matrix is obtained from 2 times of stiffness matrix. And the last option is none of these. So let's move on to the question. Which of the following holds true? That means we have to select either is any of the option, given option is or correct. So the first option is the compliance matrix is obtained from the transpose of stiffness matrix. No, this is not the correct option. This is not the correct option, because if we take the transpose of stiffness matrix, then we will get something else. That is not the compliance matrix. Is obtained from the negative of stiffness matrix. That is also not correct option. The compliance matrix is obtained from the 2 times of stiffness matrix. That is also incorrect option. None of these, yeah, this is correct option, because and none of these above options are correct. The correct answer for this option is the compliance matrix is obtained from inverse of the stiffness matrix. Because what is a stiffness matrix? So basically it relates stress in terms of strain. And what is compliance matrix? It relates strain in terms of stress. So therefore compliance matrix is obtained from inverse of the stiffness matrix. So this, if this will be the option, then it will correct. Otherwise none of these options are correct. Okay, so this is the problem number 9. The last problem most probably of this session is problem number 10. Sorry, problem number 9. So problem 9. This question says a material X X is formed by engraving two families of fibers perpendicular to each other. In an isotropic material. So options are X is an example of A option is isotropic material, option B is orthotropic material, option C is transversely orthotropic material, and option D is none of above. So X is formed by engraving two families of fibers perpendicular to each other in an isotropic matrix, and X, where X is an example of. So basically X is formed by engraving two families of fibers which is perpendicular to each other. That means we have two different properties in along two directions. So this is an example of isotropic. No, this is not isotropic because it is engraved by forming isotropic material. Orthotropic, no, this is also not isotropic material. The third option is transversely isotropic. This option is transversely isotropic. So this is the correct option, because whenever none of these, because one of the option is correct, so none of this is also incorrect. Transversely isotropic material is the correct answer because when because it is formed by engraving two families of fiber which is perpendicular to each other for the isotropic material. So this is all about question number 9, and this is the end of this session today. So we have solved multiple questions today, and each of the questions are very good question. I hope you will understand this question, and if any one of you have any question, you can ask me. Otherwise, I will end the meeting. Okay, so thanks for joining today. Let's meet in the coming Friday, which is on I guess on 8th of September. So yeah, let's meet on the coming Friday. In that session we will discuss week 7. Okay, so I hope you enjoyed today's session. Thank you. You can leave the meeting now.